Okay, it's 2 minutes past 10 here on the West Coast. So let's get started. So again, good morning, good afternoon, good evening, everyone. Thanks for joining for today's webinar on securing server-side JavaScript. I'm Arun Balakrishnan. I'm Director of Products here at Shift Left, and I'll be your presenter for today. Just a couple of reminders as we get into the webinar. At any point of time, if you have any questions, there's the Q&A chat window within GoToWebinar. So please do leave your questions there. I'll address them towards the end. And for this webinar, it's a 1-hour session, but I'm planning to leave a lot of time at the end for questions. So I'm hoping to get through all of them. And if not, we do get the questions offline. We do get as to who asked them. So we can reach out to you even after the webinar if we do run out of time. The agenda for today's webinar, I've kept it simple so I can give more time towards the hands-on demo of how things work. But I plan to cover starting off with why is securing JavaScript more difficult? Right? That's the topic of the webinar. So some characteristics of JavaScript which makes it relatively tougher compared to other languages. What some of the existing tooling does to secure JavaScript. Right? So like a quick intro into like how they work, what they look for, and why it might not be comprehensive enough. Our proposal from Shift Left as to how you can measure security more effectively, and a live demo of how that works in action. Right? So that's pretty much the agenda. Now, JavaScript is very popular, right? Needless to say. It is the most widely used language today, specifically with web applications, and on both sides of the picture. By both sides, I mean on the client side as well as on the server side. Right, so client side, like most websites do some kind of scripting within the browser. And a lot of it is also happening on the server side, mainly Nodejs based operations. It's easy to do, it's quick, not much overhead in getting some new functionality out. And that's why it's becoming popular. And it doesn't even just stop at web applications, even with things like Firefox operating system. It's been even used to write more advanced use cases. But JavaScript has differences compared to, if you can call it as traditional languages. There are some key differences, which makes it difficult to enforce security just by looking at the application code. And so the first example is this, where it is object-based language, and the object is a first-class citizen in JavaScript. For the instance, if I see this example here, say there is person, where it's defined a variable name with a value of Adam, and then also defined a function as part of the definition, wherein you call it, it returns the name. Right? So if I were to say person.toString, it gives me back the name of that variable. And then just in that next line, I can create a new variable saying person.spouse, assign a value to it, and I create a new function for it. So it is very dynamic. It is very easy to create new functionality, add new variables, add new functions. So here, for instance, this person now has a field called spouse. I set the value for it, and then I immediately can now override that value with another value. It then returns that new value. So it can be dynamically added. Now, from a functionality perspective, this is very easy for a developer. But from a security perspective, trying to infer what the code is doing at runtime, because it is interpreted, trying to figure it out makes it even more difficult. That's one. Second is it is not strongly typed, like it's loosely typed. For that, for example, here, say function add of a comma b, return a plus b. Right now, what is a and b? Are they numbers? Are they strings? And then the plus operator is overloaded, where it can do arithmetic operations, mathematical operations. It can also do string operations. It can concatenate. So if I do add and pass two numbers, it gives me the response as if they are treated as numbers. The moment I pass them as strings, it gives me a string output. Right, and the next statement, I can again pass numbers. If I could pass a number and a string, then the number would be treated as a string. So it is very loosely typed, which makes it very easy for a developer to, like accept strings and numbers from the same form in a web page. But at the same time, imagine the difficulty in parsing through this application, figuring out like what is A and B. Should I be considering them as a number, considering them as a string? So think of these where, say, let's take security vulnerabilities like cross-site scripting. Now in cross-site scripting, normally it is URLs, so it is strings. If I take a field as only a number, then I don't need to worry about cross-site scripting for that field. But in situations like these, I would need to ensure all fields are validated properly. And it also is based on context, right? So wherein here, if I do type of 0, it's a number, but at the same time, true or false is treated as Boolean. So wherein if I put x equal to 1, it is a number, but then if I do not x, then it's to be treated as a string, as a Boolean. And then if I were to do a concatenation operator with a string, then it's become a string. And so you can see that like each sentence, each statement in this code, the variable x is taking on different data types. Right? So it's very, very context sensitive, not, again, not strongly typed based on what it was initially declared as. Okay. And it's not truly a class-based language. Now, for instance, in Java, like on the example that you see here on the left side, I've defined a class, so it's person, I've given it some variables, I've given it some variables of type string, some of integer, I've defined a constructor for it, I've defined some functions with different visibility levels as to defining what they do, and then that definition is in code, so it is at compile time, and then I create instances of the class and then use it, and then do multiple operations on it at runtime. So this is for a language where the class is strongly defined, like in, say, Java, for instance. Whereas with JavaScript, it's known as a prototype-based language. So there is a concept of class, but there is no concept of defining everything in compile time within the code. It can be dynamically defined. So for instance, here on the right-hand side, similar to an example that we saw in the beginning, but then showing inheritance properties on it. So for here in A, there is a value defined, and then you create an object of A. So then some of it is inherited into B. So wherein if I do B.A, the value of 1 comes out, and then I can do C, which is an object of B. So through that double inheritance, C will also be getting some values. Then I can do D, but I'm not creating it based on, I'm not inheriting anything there. So then D is undefined because D didn't inherit anything. It didn't have an inheritance property. Right? So these are like prototype based, where it's very much again runtime driven, which makes it difficult for inferring what the developer has in mind when reading the code. So the reasons I established those 3 or 4 patterns is now to go into how a security tool looks at code and how it tries to infer what the code is doing. So most security tools, what they try to do is, in order to understand what a piece of code does, the tool converts the application into some forms of data structures, right? So it does an abstract syntax tree to figure out, okay, what is the syntax of the application, and then what are the pieces that fit into it. And then in order to understand the logic flow of the code, there's a control flow graph, right? Wherein in this situation, there's an if condition, there is a definition, and then based on the condition, it does something. Based on the opposite condition, it does something. So this is represented as a control flow graph. And then also call graph, right? So this is, again, to go beyond just functions. Where exactly is your code flowing? What parameters are being passed around? So it creates that graph as well. So this is how programmatically you can understand what a piece of code is doing. So this is how traditional static analysis software work. The existing tooling, some of how it works is, some of them stop at the abstract syntax tree, right? Wherein you create just the syntax of the application. So for instance, here, if I were to say, okay, let's look at server-side injection vulnerabilities. A signature might look like this for some existing tools, wherein they are saying, okay, we need to primarily look for eval statements in the application. What is that signature? It is saying, okay, eval, it is looking for stuff in braces. There might be things before it, there might be things after it. So you're primarily looking for the eval parameter in your code. And then it is looking, saying, okay, are these any of the parameters? So again, it is pretty hard coded, hard defined, saying, okay, is the request being used in the eval, right? And then the conclusion would be saying, okay, this is a probable server-side injection vulnerability, a remote code injection possibility, and it just spits it out. Now, the problem, as you can imagine here, is it's very tightly defined, right? Where, okay, you need to be using an eval statement, that is one, and then it needs to have one of these parameters. Now, what if this eval statement is deep in your code, right? Where it is taking in value, which did come from the user, which did come in from the request, but it's gone through some transformations, it's being passed along some objects and functions, and maybe the variable name is not request any longer. Maybe it's something else. Now that entire context is lost, right? So it leads to a lot of false positives, number one. And two, it leads to a lot of false negatives too, right? Where if I take an input, I immediately call an eval, it's going to catch it. If there is eval statements based on values that I have used, nothing to do with the user, those might be marked as highlighted as well, false positives. And then, as I said, if the variable has gone through multiple layers of your code, it's not going to come out. So that's a false negative. And then this is also, it's just regular expression parsing, right? So based on how deep you're looking, it is a lot of backtracing on the tree. So it's heavily CPU intensive. And at some point, either the application will give up, saying I've gone through enough recursions, I'm going to give up, I don't find anything in that limit. And if your limit is higher, you're going to use a lot of CPU cycles to find it. So what that means is you're going to use a lot of resources, and it's going to take a lot of time to find results. Now, before we go into deeper examples, let's see, is security indeed a problem for Node.js? So this is some statistics from the NPM package repository for Node.js. So on average, there's more than 500 packages being released every day with a lot of vulnerabilities. So 700,000 odd packages in total. And there's been over 1,000 unique advisories. So think of these as CVEs, publicly disclosed, for packages in the NPM repository. O'Reilly even has published a book saying patterns in node package vulnerabilities for developers, a book on this topic. So you can imagine this is a serious topic and cause for concern. And in terms of what kind of vulnerabilities are being exposed out of these advisories and vulnerabilities in the NPM, you can see there is a good spread, but a good amount of vulnerabilities which are pretty critical, right? So things like accessing the file system, so getting access to the server file system, which could lead to injecting backdoors, injecting a back tunnel, maybe getting data on the server, sensitive data exposure. So the application writing stuff into maybe the console or maybe to log files on the server, which it shouldn't be. Not validating inputs, which could lead to denial of service attacks, cross-site scripting, injection. So it is a good spread of vulnerabilities. So there's this a different, it's not just a single class. Characteristics leading to vulnerability. So yeah, so like some of the things that we were saying, so denial of service, regex denial of service. So like if you know that the server is using regular expressions for doing something, you could craft a regular expression as an input, wherein it would lead to the server going into a loop, trying to execute those regular expressions. SQL injection, no SQL injection, these are common vulnerabilities across applications, not just JavaScript. The information stealing I was mentioning, so wherein, say, you realize something is being written to a log file, is there a way to get that log file out of the server? Or maybe some cookie information or global variables that the server is holding on to. Even things like, say, AWS keys or API secrets, can we get hold of that? And the common thing is also using components with known vulnerabilities, right? So a lot of vulnerabilities are from how the developer has written bad code, but also vulnerabilities leading from using components which have known issues in them. So let's look at an example which might fail with the traditional approach. So in this example here on the left-hand side, you have like a 30-line snippet of code. It's taking in, so it's defining, saying, okay, I'm going to use some HTTP URL-like functionality. I've created a server. It's taking in some request and giving back some response. There is some URL information that is coming in from the request. I'm going to parse that. I'm going to log some of that into my log. And then say if the URL has read, so think of this as one of your API endpoints, I'm going to do an operation. So here I'm going to move money from point A to point B. And then I'm going to be listening on port 8080 to do all of this. And then for the move money function, I'm going to be taking some input from the user, and I'm going to be evaluating it based on that input. So how traditional vendors work today? The first piece is software composition analysis, wherein they might just say, okay, hey, I see that you're using some libraries here. I will look it up against like the version that you're using, look it up against a CVE database, and inform you if there are known vulnerabilities in these libraries. Right, so that is one piece. So that ends there. And then for the vulnerability analysis vendor, what they would do is they would look for parameters like this eval, the example that we saw before. And then here is the example I was talking about, where the input is data, right? So what came in as request was parsed and then passed on to a function where it took into a different variable called data. And that variable data is what is passed into eval. Now, in that previous example, when I'm looking for a request, this would fail because it doesn't have that pattern. So this would be shown as a false negative. And then in this situation here, if you look at this, it is pretty much writing everything into a log file, right? That log, the URL parts. So imagine if this request is this move money, maybe it is, say, a hashed version of an account number, or Maybe you're not even doing a hash. Maybe it is account number in clear text. It is all being logged, right? So now if I get access to this log file, I can get a lot of sensitive information out of your server, right? So, and it doesn't catch that because that pattern was only looking for server-side injection with eval statements. So the primary difference as to how we address it here at Shift Left is a different approach to static analysis or code analysis. The main difference in the traditional approach is, if you remember, they were looking at only at abstract syntax trees, wherein you don't have that context, right? So you are looking at a piece of code. You don't know what happened before this. You don't know what's happening after this. For that, you need the other data structures I mentioned. So one is control flow graph. So I don't know if there was a statement made before this. So I don't know if there's another tree to the side of this which would occur if the evaluation is wrong. So I need this information, and I don't have that call graph information. Wherein, say, in this previous example here, where the value was taken out of the request, passed on to a function called move money, and that is where the value is being used. This information comes in only if I have that call graph information, or I would be looking at this as an independent piece of code. Right? So you need that. And then you need that whole understanding of the context, right? So you need to understand what is user controlled, right? So instead of just defining, saying, okay, I'm looking for a rec, meaning request, I need to understand that why request is important, right? It is something that can come in from the user directly, so it is attacker controlled. So this can be treated as a source, which is sensitive. And then I need to be able to track where it flows, and then I need to see if it is being used in a way which is insensitive or which is attack prone. Right? So that semantic data overflow, overlay that, and we need all of these to work together to make sense. And that is what we have done. Right? So we call it a code property graph, wherein what we have done is effectively overlaid all of these information into a single data structure. So you can see, like in this data structure here, in this graph representation, we have the abstract syntax tree, we have the control flow graphs, we have the dependency included in this. And then on top of this, we've even layered on the other information saying what are HTTP endpoints, what is touching a database, what are patterns that we should be looking for. So all of that information is in a very dense graph representation, which is what helps us do what we do. Now, what is that we do? So in this example, so if I were to go back here, it was pretty much just looking for two things. With all that dense information that we have, we can go a lot more beyond that. So one, first is to understand, again, the software composition, saying, okay, yes, we are using HTTP, URLs. Okay, that gives me context saying, okay, this request and response variables are important for me. So that is one, right? So wherein I can then get context saying, okay, I'm creating a server, I'm taking an input, that is going into a log file, so that is tricky. So let's go step by step. So one is SCA context. The second is I know what are attacker controlled variables and parameters, so I understand that. Then I understand what is the entry point for an attacker, so that we treat as a source. And then with that, I also understand what is happening in the code, saying, okay, hey, this is now being written into a console. It is flowing into that, which is considered as a sensitive sink, because I don't know if this log file is encrypted in motion, in rest, who has access to this log file. Is there a way for me to retrieve this log file from the server as an attacker? So this can be classified as a sensitive leak. And then I understand this, saying, okay, this is an API endpoint. So this is the attack surface of the application. So I should be monitoring these more critical because these are accessible to the end user. And then I can see that this information is flowing in. So now this information moved into a function. So there is a control flow here. So I can then treat this in context of what came in from the attacker or the endpoint. And there I'm looking at saying, okay, I see an eval function being used. I see that data coming in actually came in from all the way from the beginning. And this then is a candidate for server-side injection, right? So now I've found the whole flow and pattern. And this then helps me define a signature saying, okay, so now with this in place, this could lead to a server-side injection wherein I'm writing maybe, say, access the password file, convert it into a string, and spit it out back to me, right? And then this is now going to give me hashed passwords for all the users on the system, potentially, if other controls are not put in place. Or I could possibly do a command injection, right, wherein I could launch a file as a child process of the server, and that could establish a reverse tunnel, right, wherein once that is established, then I have a always open tunnel into the server where I could maybe, like log in over SSH or like do some operations without having to use the web application. So looking at this code, thinking as an attacker, if I had access to the source code of the server, this is how I would be thinking, right? Where I see all this flow happening, I would say, okay, in this move money function, using the request parameter in the public API move money, I can do these two operations to attack the server, right? And this is how the static analysis should also be thinking to prevent these attacks from happening. So with that said, let's see this in action, how this would happen. So for that, okay, I've got our tool Ocular running here. Screen. So Ocular is a shift-left application. It works off the code property graph, which helps you convert the application you have into that graph representation I mentioned, and then run queries on top of it to figure out if these patterns exist in your application, right? So to see that in action, let's do this. So I've got a source code here as part of an application called exploit node application. I've got a bunch of vulnerabilities written in this, and one of that is remote code execution. So similar to what we saw in the example here, wherein I've got some endpoints, and in this endpoint, say for instance in run, I'm calling a function called runMe. I'm taking this request, I'm translating it into command, I'm passing this command. It comes in here, and then that command is used to spawn a child process, right? Now, this is a classic example of remote code execution because whatever is being sent by the user as run will be run on the server, right? This is bad code. I mean, nobody should be doing this. But even if someone were to do this, how do we catch it? So let's do this. So I've got a bunch of commands here. This is how we start. Let me show you line by line. So first is to define saying, okay, I'm looking for spawn, right? I've imported the code in this directory. So I'm going to create that graph using this. So let us just run through it. It's going to create the graph. And then once it's done, let's go back to this one. Once it's done, I'm going to look at all the sources, right? So I'm going to tag it in our graph. When we create, we already have ways to figure out what are the sources. Those are marked as expose methods. So I'm going to get that as a list. And then I'm going to get all the things which lead into this function. And then I'm going to ask the graph saying, show me ways to reach this function, reach spawn, show me where all it is reachable through, right? And then if it is from an expose method, that is a potential command injection. So there you go. So if I were to execute that command saying show me sources that leads to this sink, it says, okay, in this file, vulnerabilities exec.js, it starts on line number 27 in this request parameter. So I have this file here. Let's see if that is true. So yep, here on I forgot the command to show line numbers, but here. So in request, I've got the endpoint coming in, and then it says it is being assigned as parameter 2. It is being assigned, and then it is calling function run me. So that is exactly what is happening here, wherein that value is being assigned, and then it is calling the function run me. And it is then showing that it is calling spawn with parameter number 1. Right? And that is exactly what is happening here, saying calling spawn with parameter number 1. Now, you might say, okay, let's test this. Let's give it some more examples and see if it is able to catch all the possible options. So I created one more file here saying no vulnerability, right? So I've created something similar, wherein I've created another endpoint called test. And then here also I'm taking a request. But here, instead of taking the request, let me just spawn, and I'm just directly calling ls as a command, right? So I'm not taking any user input. And this file is also in the same application. So this flow did not show up when we ran this command, right? So this is not in the list. So when I run the command, it only shows me the flow in vulnerabilities exec. Now, if I were to change this, so if I change this and say, okay, let's not take a static variable. Let's take the user input, right? So let's take the input directly, saying let's do request directly. So you can see here, the request is coming from the user into the endpoint test, and then that is being directly passed into spawn. Now let's see if the graph will pick that up. Now I change the code. I save the code. In the real case, it will be say commit into a repository. And to make it take the new code, we'll have to again create the graph. So I'm going to import the code again, right? I'm going to recreate the graph, and then I'm going to run the query again. And this time, let's see if that flow is picked up. So it's created the graph. It's created the sources and sinks again from the graph. And now let's see if the flow is shown. And there you go. So now it says, okay, the one and no one function is also an issue now, wherein it is taking request and it is passing as parameter number 1 into spawn. Right? So it is immediately able to catch saying this file also has a vulnerability now. So now let's test it a bit more, saying, okay, I'm passing it in request. Let's pass it. I'm going to pass it into a variable and pass that variable instead. Right? So this is where most of the other tools will fail immediately, wherein it doesn't realize that request was passed into command and command is using spawn because it only looks for spawn request. So just one line might trick other tools. Let's see if Ocular can be tricked with this. So save that file. Again, go in and recreate the graph. Okay, and then let's see. Okay, I got a feedback saying this is not viewable. Give me 1 second when I make this bigger. Let's go even bigger. Okay, and then let's make it zoom in. Okay, right, so I've zoomed in. Let's see, this thing doesn't work at full screen. Hi, give me a second. Okay, there you go. Okay, right, so now I ran that command again. And then, so to go back to that file, what we did here is I said, okay, let me take request. I'm going to pass it into command, and then I'm going to use that variable to spawn. And Ockler said, yeah, we'll catch that too. Wherein request came in, request was assigned using an equal to operator, and it was assigned into command, and that command was passed into spawn. Right? So now let's try to trick Ockler with another situation, wherein let's say, okay, so now let me not take user input into command. I'm going to take a static code. I'm going to say call ls, but I'm going to call it into command. And that is the variable I'm going to pass into spawn. Right? So now no longer is it user input, it is inside the code. Right? So it's not attacker controlled. So I'm going to save this file, go back into Ocular, and recreate the graph and run the query again. In the meantime, if you have any questions, feel free to send them in the chat window. Okay, so now when I ran the query, the other one has disappeared, right? Wherein Ockler knows that, okay, now what we have done is just put in a string into command. It is no longer dependent on the user input, and hence it is not susceptible to remote code injection because the attacker cannot control what is being passed into spawn. Right? Even if it's a variable, even if it is flowing in your code, we are able to track saying this is benign, not user controlled. Right? So this is the power of the graph when you combine all those data structures. So going back into this, the presentation here, like this is pretty much the example where we were saying, wherein in the example of traditional static analysis, it would be just focused on this line, and it might see eval and then just immediately say, okay, it is an issue. So it's a false positive. Wherein what we did with Ocular was continuously change all these flows, change what is going into eval, put eval statements with hard-coded strings, put eval statements with variables with hard-coded strings, take it from the request and pass it, and it is catching the right ones, right? So you saw there were no false positives, and there were no false negatives in the examples that we just saw. And so this is the way that we run Ocular, where it is a on-prem solution. It is running on the on a workstation on your premises. We also have a SaaS-based solution, which is called Inspect. So I ran the same application. So for this webinar, I ran the same application. And here, if I zoom in this one also found the same vulnerability, right? So it said, okay, hey, executing OS commands is security sensitive. So on line number 35 of this file, vulnerabilities exec.js, it said, I am spawning the operation with the command running. So this is what is in this code. So if I were to go into exec.js, it is running command running on line number 35. So this tool, which is SaaS-based, also runs off the same graph as the same kind of analysis. But then you don't need to take care of the infrastructure. All of that is running on the shift left infrastructure. And it is not just limited to this one use case, right? I mean, there are a lot of use cases detecting SQL injection attacks, cross-site scripting. And this is for JavaScript, but that doesn't mean it's only for JavaScript. It also works with other applications. So for instance, this is a Java application, right? Where if I were to go into vulnerabilities, it gives you detailed information complete flow, including things like sensitive leaks, right? Wherein it says, hey, I'm writing customer information into a log file. I'm writing like account information or like patient information into a log file. Gives you descriptions of like why this is an issue, links to tools where we know how to fix them. So for instance, if I were to like take cross-site scripting, it gives you like complete flow information, including line of numbers. So if I were to click this, it would open up the GitHub repository. This is based off an application on GitHub. So it directly jumps me into the line of code where the vulnerability is happening, right? So it gives you that kind of information. And then if I were to go into description, I click on the link, it opens up information on training the developer on, like why is cross-site scripting happening, why this is, what leads to these vulnerabilities. And then this page also gives examples, language specific on how you could take care of these vulnerabilities, right? So for instance, say if I were to go into mitigations, like if it's JSP, it said, okay, before you do this, like validate the string before you use it. So it gives you examples of those as well. And then, so yeah, so cross-site scripting, sensitive leaks, it does all OWASP top 10 vulnerabilities, SANS top 25 vulnerabilities. It also integrates into your workflow. So for instance, you can assign it to other users, you can integrate it with Jira, then you can send it to Jira. It also easily ties into your CI/CD environment, right? So by that, what I mean is if I were to go into GitHub and look at the application that is scanned here, and if I were to look into my pull request, so this file, for instance, here, it is automatically, so when I go in here, when I made a pull request, as part of the pull request, here on this one, it will say, okay, I'm creating the pull request. The pull request cannot be approved unless some checks are validated. And what are those checks is it tries to build the code and it automatically performs shift left code analysis. And then this code analysis is what the results of that is what you're seeing here, right? And then in this code analysis, it failed. It failed because here, if I go back to the comments, it said shift left found vulnerabilities that violate policy. Go here for more details. And then this dashboard is what you're seeing. And it can even fail the pull request, wherein most organizations, like this is my private repo, so there are no other assignees, but most organizations, when I make a code change, someone is going to be reviewing that code change. They would be seeing this conversation. They would see that, okay, something was found. Maybe I'll go and fix the code. I'll shift left will reanalyze the application. It will say, okay, vulnerabilities are now fixed, and then checks have passed. So the reviewer will automatically know that, okay, static analysis has already done its job of validating. The developer has done their job of fixing stuff. That makes my job easier of reviewing the code. Right? So this is GitHub integrated with Circle CI. But then if you were to go into our docs website, docs.shiftleft.io for inspect, you can see here integrating code analysis into existing workflows, right? So Bitbucket, GitHub, GitLab, Circle CI, Jenkins works with everything. So like I've also integrated with CloudBees, which is Jenkins for enterprise. They have SaaS products. They have the Jenkins on-prem. It works with all of those. And then it works for multiple languages, right? The JavaScript is what I demoed, but it works for more languages. And here you can see the software we are talking about, so Inspect and Ocular, the demos that we did. So you can go over these. And one thing I wanted to tell you guys is this one is shift left inspect has a free account option. It's absolutely free to use up to 200,000 lines of code a year, 300 scans per year. You can go to shiftleft.io/register. what you saw was capabilities from the security perspective, but there are also capabilities which not part of this webinar. I wanted to cover more of the capabilities and for JavaScript, but there are points like how we can very quickly analyze a lot of code, like up to 1 million lines of code in less than 15 minutes. You saw the OWASP top 10, the sensitive leaks. It also does hard-coded secret literal detection, helps you do prioritization, the pull request integration that I just showed you, the languages that it supports. And then, yeah, it's a free account, so feel free to check it out. So any questions? We've still got around 12-13 minutes. So a good time to ask any questions you might have. I see a few questions come in, so let me start taking them. So the question is, yes, does it detect other vulnerabilities like SQL injection? Yeah, so the demo that I showed you was for command injection. I wanted to spend a lot of time on one vulnerability so I can do all these different use cases. I didn't want to be just a demo of all the things that we can do. But yes, very much do SQL injection, vulnerability detection as well. So if I were to go back into this example here, if I were to pick, let's see if this one has any SQL injection. This one doesn't have any injection vulnerabilities. So yeah, this application doesn't, but yeah, it very much does do SQL injection, cross-site scripting. So all of these examples, right? So OWASP, all 10 categories, all the SANS top 25 categories, it does all of these. Yes. The next question is, can you do custom detection? Yes, definitely. Yeah. So I'm assuming you mean to say custom in the sense make it more relevant for your code. Yes, absolutely it can. So here again, going back to documentation, say for instance, in inspect, I believe it was in customization. Let's see now. So dashboard. Okay, I should be using search. Okay, so sensitive data variables. Yeah, right. So there's complete use cases on how I can do custom policies. So for instance, in this example here, here it might say, okay, I'm logging request URL into a log file. Maybe I'm like changing it to different variables and I'm logging those. So I want to catch them. Yes, you can absolutely do that. Our policy file, our dictionary file is open to customers to use. So what that enables is you can define these, saying, okay, we've already defined a lot of variables for you to use what we think are sensitive, but there might be variables that are more applicable to you, so you can easily define them. So that's one way. And then you also can go on to define custom policies for custom vulnerabilities as well, right? So in this example here, in this script, what we were looking for in Ocular is saying, are there exposed methods? Let me zoom this in a bit more. Right? Are there exposed methods that are a source which go through your code and end up in a function which calls spawn? Right. So this is very unique to command injection, but yes, you can do these for. I mean, we have these policies predefined. I mean, this is just an example to show in Ocular, but we have these policies predefined. But if you are looking for specific functions, if you say, okay, hey, there is this internal function saying get credit card number, right? And then I want to see who all can access that function. Where all from your code can that function be accessed from? So it wouldn't fit into a standard SQL injection or cross-site scripting kind of tracking, which is why we wouldn't have that policy. But you can define it, and then all those flows would then appear in Ocular and in Inspect, right? It'll track this. It'll give you line by line flow information of what is happening. Yeah. Let's see. Questions. Okay. How long does it take to scan a 2 million lines of code project? So what we define as 1 million in 15 minutes, that doesn't mean that 2 million is going to be exponentially higher. To give an example, it is 500,000 lines of code happens in less than 5-10 minutes, and then 1 million in 15 minutes. The biggest one I've experienced with the customer is like, I think 1.8 million lines of code in like 27-28 minutes. So I don't have an exact number for 2 million, but I hope that'll give you a context of how much time it might take for 2 million lines of code. One question is, do you support incremental scans? The reason we don't need to is our speed, right? So yes, we have encountered competition where they say incremental scans make it faster. That speed is in some cases even slower than what we do for full scans. That's one. Second is, I mean, as a developer, you can imagine, right? Like if I change a line of code, the implication of that could be local. The implication of that could be global. By that I mean, if I change a line of code, yeah, maybe one function has changed. In that situation, incremental scan makes sense. But if I change a line of code, the entire application might change behavior. In that situation, not doing full scan is meaningless. So that is one. And second is, we've also heard from customers who have started using our solution after stopping incumbent solutions. Most of those legacy vendors, even if they're doing incremental scans, they do force you to do full scans every 3-4 scans, right? Because I mean, the percentage of code has changed where without a full scan, the results might be meaningless. So overall, when you do average time, it is still very time consuming with other tools, right? So that is, so with us, you're only doing full scans and then those scans are fast. How many lines of code are you scanning when you're running the query? So in this example, it was few hundred lines of code. This application is not that big. But the queries, when we run, we are doing it against the entire graph, right? So by that, I mean, the moment the graph is created, so wherein I have like the CPG here is created. Okay, the CPG is created, and then this code property graph is present. All of these queries are on the CPG, which means for the entire application, right? We are not doing on parts of the application. So the CPG creation is what takes time. So if I say 15 minutes for 1 million lines of code, say 5-10 minutes of that would be the CPG creation, and then in our SaaS product, we run like 60,000, 70,000 different queries and policies on it before we create the dashboard. Similar things can be run here as well. And then if, for example, here, if I do this command, yeah. If I do this command, it's like a pretty print of all the findings. I think I should have just listed it. Okay, and look up that command. But then the thing is, this Ocular also runs all these queries. So the inbuilt queries that we have, it does those as well, in addition to the specific queries that you are asking off the graph. Okay, so how does Ocular compare with tools like SonarQube or Fortify? So I think the primary difference, going back to the slide, is this one here. is the depth of analysis, right? So a lot of tools out there are restricted to the abstract syntax tree representation, right? So you're like very limited in what you're analyzing. So that is a primary difference. So the depth of analysis is way more for us. And then you can also look at our website. There is a white paper that we've written where how we came up on top of the OWASP benchmark, almost like 3 times more accurate than competing solutions. Accurate in the sense, the number of vulnerabilities we find, so true positives, the number of vulnerabilities which are a mistake, so false positives. So a combination of this, we are on average 3 times more accurate than all these legacy vendors. That is primarily because of our depth of analysis. So like this code property graph. Will a recording of this webinar be available? Yes, it will be. I think you should be getting an email to your link. How is this different from Vera code? So similar to what I mentioned for SonarQube 45, it is the depth of analysis. Explain the output table in more detail. Definitely. Oops, I clicked the wrong button. Okay, so this one. So this one, so for the output table, this is what is being tracked. So this is the variable name. So if I say request, I go back to the source code. It says, okay, request is coming in on line number 27. Yeah, line number 27 here, right? In the source code here, if you see, it says here 27. So request is coming in on line number 27, and then that is what is being tracked, right? And it is being assigned into the variable command on line number 28. So that is exactly what is happening here, saying command is being assigned the value of request. And then it is being tracked, saying it is going in as a parameter in command. It is going into function run me on this line number. So again, here if I say this command is being passed as parameter into run me, and then within run me, it is calling spawn function. Let's see now. So that is line number 35. Yes, so line number 35, run me is calling spawn function, and this command becomes parameter number 1 for spawn. And let's see, it's becoming spawn parameter number 1. Okay, so this is the tracking that we are doing in this table. Do we support Python? It is scheduled for later this month, so yes, we will. Is there a suggested fix when we find a vulnerability? So yes, so those links that I showed in the UI, similar output is available in Ockler as well. So those links will tell you where that output is. We're on the top of the hour. Let me take maybe one more question. Okay, how often do types change like that at runtime? It very much often does. In JavaScript, developers, if they have an option, they take the easy way. They don't keep defining variables. They might say, okay, this field supports both integer and text, so let me just take one variable and take both, right? So yeah, it often does change. So yeah, we're at the top of the hour. There are a few more questions, but we know who's asked them, so we'll reach out to you after the fact. Thank you again so much for joining us today. As a reminder, going back to this slide, please do check out our website. Please do sign up for a free account. And thank you so much again for your time. And I really hope this was useful. Thank you again.